Okay, so two things that are very important about your makeup lecture. For last Thursday, we got your programming test number 1. So to really study for the makeup lecture, as I pointed out before, if you go to the lecture site, you will see that right here, makeup lecture right here for programming test 1. That one there introduced you to about abstract data types and also stack, the last in, first out. So please make sure you study that in time. And I'll confirm about the coverage of your written test that's coming. And then just make sure you study for that, right? It's very important learning outcomes to satisfy. And if we look at the semester calendar, let's look at that together. Now that we already finished your first assessment. And let's see here. Yeah, the connection is a little bit slow today. Just bear with it. Bear with it. Okay. All right, maybe it's still loading, but I can mention that to you just right here. All right. So for the this week, we have no assessment, and also for next week, you don't have any assessment either. Okay. So on March 19th, you will get your written test. And also on March 26th, you'll be back-to-back week, right? That's already confirmed since the beginning of the semester. You will have your programming test number 2. All right. All right, just notice that these are the 2 more assessments coming before the final exam. And your assignment number 3 has just been released yesterday evening. So make sure you actually complete it in time. So assignment number 3 will be the basis for your programming test number 2 about trees. And part of it is really use the singly linked list to really as the child list. You will see, right? Something I will also talk about today, so you also get more intuition about how to solve things. But the example that we use in class about trees is not exactly identical to what's happening in the assignments. So to really get prepared for your programming test number 2, you want to focus on assignment number 3. All right, that's something you want to focus on. But for the lectured example that we're going to start talking about today, you want to focus more for written tests and also the exam. Okay. All right, let me just see if it's finished loading. Okay. If no, that's okay. Well, somehow just the server for EECS a little bit slow today, but let's not worry about it, right? The calendar is there. Nothing has changed. Guys, any questions before we move on? Okay. Okay. Very quick recap from last Tuesday. Okay. And then we'll move on. All right, so last Tuesday, we started talking about the trees, abstract data type, what's really a tree. And we first clarified about what's the difference between nonlinear versus linear data structure. So linear data structure would be when you got unique successor or unique predecessor as well. How do you violate about linear property? If you got multiple predecessor or multiple successors, in that way you will violate the property. So there are 2 data structures that will violate it. One will be about trees over here, right? Predecessor, like going to the parents, it will be unique, that's okay. However, for successor, it will be multiple in general. So that's going to be not linear. And also in 3101, you're also going to learn about graph data structure. That one there is also going to be non-linear because you got multiple predecessor and multiple successor. Just focus on this table here, right? Just talking about what does it really mean to be non-linear versus linear and what are the different kinds of data structure that will satisfy either way. Okay. Any questions about this? It's very important, classification. And then we spoke about the various terminology about trees. So root, parents, children, siblings, and also ancestor, and also ancestor path. That's something we'll also need to focus on when we talk about some tree operations later. So ancestor path, also make sure how you know that how to compute it, and also descendants. Okay. And then subtree. So subtree is the most important concept to really understand when you want to do recursion. So that's something you will see when you do assignment number 3. So whenever you want to solve a problem on a tree usually the size will be too large for you to really handle right away. So you have to somehow handle the root first and then handle individual subtree separately and then combine the result together. It's a little bit like you're given an array that's too large to handle right away. Handle the first elements, and for the rest of the array, you handle that in a recursive call. Now in the tree case, you got to handle different subtree in separate recursive call. So that's the difference. And we talk about just going over how you can count the number of nodes recursively, right? We start counting the root right here, and then it's going to recursively count how many nodes there are in this particular subtree, and how many nodes there are in this particular subtree, add them up together, plus 1 of the root, and then you get a result. We did a detailed tracing about this one here. Make sure you go over it. I think that can give you more intuition. But for today, we're going to do one more similar example like this. Okay, one more. Right? But for counting, it's pretty straightforward, but also very foundational. Right? If you can understand this, you get a very good intuition about how you can split the subproblems into different subtrees and make a separate recursive call. Okay. And then that's about counting how many subtrees we have in total. And then we talk about how many subtrees corresponding to what size. Right? That's the exercise we did also as well. And talk about external versus internal nodes. External nodes will be all the nodes without any further child right here. So these will be the typical base cases. And for internal nodes, for example, David over here, we got at least one child that will branch out. In that case, you have to handle them recursively, right? It's not a terminating cases, right? External versus internal. And we got edge and path. Each link over here will be edges. And the immediate relevance would be, let's say, given Peter over here, we're asking about the depth of Peter. In that way, you got to count how many edges there will be in total. Go from Peter all the way up to David, the root. So here you can see edge number 1, edge number 2, and edge number 3. So 3 edges. So that means the depth of this particular Peter node will be 3. Okay, so that's about the depth. And we try to distinguish between what's really the depth of a node versus the height of a tree. Right? Notice that the applicable object is different. One is about the individual nodes. The other one is about a tree. Right? So that's very important as well. Just make sure you go over the definition. And according to the depth of each node, we can somehow divide your tree into different levels. So level 0 contains all the nodes with depth 0, which is only the root, always. There's only a unique root. And also you got those nodes with depth value 1, and etc. You can divide them into levels. So either today or Thursday, we'll get into when you got like a specialized kind of tree called binary tree, then we will be able to somehow figure out more patterns about how many nodes you have in each level. But when the tree is kind of general tree, you have arbitrary number of child nodes for each node. It's not exactly like a patternized, not as easy, but we'll get there, right? But for general tree, just remember, you may get arbitrary number of nodes for each node as a children. Okay? But we're going to see the more specialized kind today as an introduction. All right, so this example here, just to show to you, if I ask you about the heights of, for example, this particular tree versus the height of this particular subtree, the result might be different. You got to make sure you figure out the maximum depth of the descendants of that particular tree, right? It really depends on the context. Okay. All right, I think that was the last bit. Guys, any questions about terminology? Any part you want me to clarify or redefine? So these are all important, right? So you got to make sure you can learn them and then apply them, right? All right, let's now move on with the lecture. Okay, so I will start from slide number 10. Okay, general tree, right? So we already talked about terminology. Let's now try to make things a little bit more abstract. You want to think about trees in general, right? First of all, tree in general is recursive data structure, meaning that you have base cases. Also, you got recursive cases. Let's see how we can visualize it. I'm going to just go from scratch, but you can also look at the slides. Okay. So once we understand about the layout for general tree, when we get to the later part of today's lecture about binary tree, it will make more sense. Okay. So there are two cases, basically. That's kind of like base cases. Case number 0. When the tree size is 0, which means an empty tree. There's simply no node in the tree. So we got case 0. The tree that we are talking about is simply just empty. Empty tree. Okay? Conceptually, you can think about this symbol here. It's like an empty set, as you learned from the previous math course. Or you can think about the root attributes for the tree is simply pointing to null. And at the same time, let's say if we got some size attributes, it will be just 0. Right? So that's how you can think about empty tree. Empty tree usually will be one of the base cases. For example, if you want to count how many nodes there are in an empty tree, 0. That's something you can return right away. Another case for base case would be when you got something called singleton tree. There's only one node in the tree, and that node will be the root at the same time. So case number 1. So a singleton tree. So you will be hearing about singleton tree, singleton graph, or singleton list. That simply means you got only one element in that particular collection. Okay? So how do we visualize this? There's only one node. Well, diagrammatically, think about there's only one node. I can just draw one circle. But let's think a little bit more programmatically in Java, right? So for the root attributes, it is going to point to some tree node objects. I will keep this part a little bit vague and abstract just for now. We're going to look at the Java code today for sure. Just bear with me, right? Let's just think about conceptually. We have some object here, and root is pointing to it. And it got various attributes here. One of them is called children. Since we are building a general tree, which will be the case for your assignment number 3, 4, and also programming test 2. That means the number of children here is not restricted to 2 for the binary tree case. It can be arbitrary. So what will be the most obvious way to really store the children? It cannot be like a left and right, right? It's only like a binary tree case. It has to be like a list, okay? So over here, in the case of there's only a root node right here, that means it has no children. So there are different ways for you to represent there's no children for this particular node. Either you can say the children here is simply pointing to null. That's one way. Or you can say the children here is pointing to an empty list. That also means no children. Okay, already done. Or here you can say it points to maybe some array list or array, right? Doesn't matter as long as it's a collection. It can be array list of tree node, which is closer to what you have to do for your assignment. Okay, tree node. Okay, and it could be just empty list. Well, empty singly linked list, empty doubly linked list. So this part here, either to pointing to null or pointing to an empty list is completely up to your implementation. It's more like a choice you have to make. Okay, so either we go for empty or we go for null, right? It depends on how the JUnit test cases was set up. What's the expectation? So this is more like an implementation decision. Implementation decision. Okay, so you can look up your assignment number 3 JUnit test cases to see which one it is. But if you're doing your own application, you can choose between as long as you keep consistent. Okay. All right, so that's about singleton tree. Okay, I'll make it a little bit smaller. And then let's now talk about the recursive case. That means that, let's say we got more than one nodes, at least 2. Right? So that means we've got to go to maybe level 0 and level 1 and so on. So case number 2. When you got at least 2 nodes in the tree. All right? And then we have to somehow to see how is this structure recursive. Recursive in the sense that the structure is going to repeat itself in the subtree. But we're going to see exactly how. Okay? Let's now just draw something here just to get some abstract idea. If I got my root over here, right? And then I got at least 2 nodes, that means I got to go to level 1. Okay? It could be that I got maybe the first child right here. And then I got my second child right here. And I can get as many as I like. And then I go to the last child right here. So think about right here, we got n children. More to it, every child over here is the root of a subtree. So think about this one here is a subtree. So this is a subtree rooted at the first child. And this one here, for example, right? And so on. this one will be a subtree rooted at the last child. So this is how we can view this structure here as recursive, because the root itself has a tree structure. And this subtree here, rooted at the first child, also has a tree structure. It really repeats itself, just in a different scale, right? So that's why it's recursive. Okay. So this is really a recursive structure. But we ought to see how this can be implemented at a runtime, right? Let's take a look at that. Okay. I think this will also help you for the assignments for later. Let's just see the first version. Okay. Let me start with, let's say the root, let me use red right here. Okay, right here. Okay, so this will be the root. Let me draw the root right here. The root is pointing to a tree node right here, right? Pretty much like the singleton tree case. Okay, let's start with that first. And then we got various attributes. One of them is children. And let's say for now, we are basically using an array to store all the children, right? Index 0, index 1, all the way to certain number. Okay. So think about, we got an array over here. Index 0, index 1, index 2, all the way to maybe n minus 1. Let's say we got n children. You can think about here, this linear collection of the children is like this array here. Array itself is linear, right? You can see the correspondence here. But now we want to see how exactly can we reproduce the individual subtree. Right? There's no magic here, because each individual slot in the array is going to store the reference of the root of some subtree. Right? Let's take a look. So one of them, let's say this subtree. Let's make it orange. Okay. How do we represent this particular subtree? This will be the leftmost, which will be index 0. That means this one here, index 0, is pointing to the root of the first subtree. That one there is just going to be another tree node. And the tree node over there has various attributes and itself may also have children. And that one there may also have a list of grandchildren right here. So the structure really repeats itself. So think about what we're having over here can be represented by this starting point. It's a subtree. Okay. And then this one here, for example, the last child. Let me use purple here. Okay, this part here. That part there just repeat itself. Again, the last child here is pointing to the root. And that one there also has some grandchildren, which will go further as an array. Okay. So this will be the first subtree. And this part here will be the last subtree, and etc. I'll make it a little bit more concrete since we haven't seen any Java classes just yet. But I think this one here ought to give you some correspondence. This is how you draw the tree diagrammatically. And this is how you are supposed to create different objects of tree nodes type and then try to set them up. That's something we'll see as well. Okay. Guys, any question so far about the tree? All right. We'll try to go a little bit more slowly, right? So this is not exactly precise, but we'll make it more precise as we go to some Java fragment. Okay, we'll get there. Okay, so that's about a general tree, and there is a notion between order and also unordered trees. Okay, let's clarify that very quickly. Okay, so just some example about legal tree and also illegal tree. So that's something we spoke about last time, right? You got to make sure. So for example here, for me to go from the root all the way to some node, there's only a unique path. On the other hand, let's say the top node over here and the bottom node over here. There are actually more than one way to really go there, right? You can see it's more like a diamond shape here. So that tells you it's illegal tree. It's actually a graph, which we don't really cover in this course. We'll do that in 3101 later. Okay, good. And order tree and unordered tree, right? Just an example here. Okay, let's now make some annotation here. Okay, so let's now make some comparison right here. Okay, so order tree right here, where the order of the children matters, right? For example, let's say we got a book being the root, and the part A should really go before part B, and part B should really go before the end of the book, which is about references, right? The order really matters, right? So you just gotta judge to see which one you want to go for, either order or unorder, right? So how can we store? For example, this can be an array, or it can be array list. Can be singly linked list or doubly linked list. Right? Unorder would be, let's say, directory structure. If you actually log in, that's something I would encourage you to try. Maybe, I'm not too sure if you know this command. I cannot really connect to the server, but this command is actually available there. I'll just run on my Mac to show to you. Let me just show you. There's a command called tree. So relevant. Let's say I'm not in my current directory here. If I say tree, it's a command that will work on your Indigo, your REST server. Just log in and try this command. Okay? And I say I want to get a tree structure for my current directory dot. If I hit enter, it's going to show me the tree structure. For example, this will be a directory. Underneath it, I actually got the individual file. It's like a tree structure. Right? So that's something you can give a try. It's a very, very nice way to visualize your directory structure. Okay? However, we're just assuming that when you actually got the individual directory here, the order doesn't really matter. Right? There's no logical order to say this directory should go before that, let's say, in our context. Okay? So here, if you actually, let's say the order does not matter. Okay? A very obvious choice is you can maybe use a hash set, for example, for storing. But if you really want to use a linear collection like an array, singly linked list, that's also fine, as long as you don't really impose any order when you process the tree, the children. That should be okay. All right, just very quick distinction. Okay. All right, so let's now look at some Java code to see how we can construct trees. All right. So this will be, let's see the slides. Slide number 14, right? So 14 over here will show you the tree node class. And there is one particular line I want to spend a little bit of time, not too long, just to show to you. Java here does not really support generics 100% intuitive, but there's some trick you have to write the code. I'll show to you when we get there. But the tree node class itself is pretty straightforward, and you will do something similar actually in the assignment. You will see once you stop working for the test cases. Okay, and then we got the various methods there. Okay, I'll go over them in a moment. And then, so we're gonna also go over this fragment of code just to see how we can construct a tree from scratch. Right, that'll be important. Okay, so let's look at these two fragments. Okay, closely. Just to start with, we have the tree node class. And you can see that this class here is generic, which means the E here may be instantiated to any class you like. You want to say individual node may store string, may store integer, or it may store person, right? So this will be instantiated to, for example, string, could be person, etc., as long as it's a known class name in Java. And let's look at the attributes. First of all, you can see that the elements for each node, the type here, E, here, just correspond to E right here. As soon as you instantiate the E to be, for example, string, this will be instantiated as well to be string. Right? That's something in the background for assignment number 3. Make sure you go over the background about Java generics. You will need that for sure for your programming test. And for every node, we got 2 references. You can think about going up to the predecessor and going down to the successor. Okay? So this part here is about going to the parents. There's a unique parents node. At the same time, it's called predecessor. On the other hand, you also got an array, like a linear collection of children nodes. Okay, a list of nodes. So we got multiple successor. Okay, I'll visualize very quickly in a moment, but let's just go over attribute very quickly. And since we're using array here, okay, let me just highlight it. You can see we got array, but in your assignment number 3, okay, so you got different choices. In your assignment number 3, it's a singly linked list. Just make sure you can do both. The way you can implement this stuff will be very similar. It's only about how you can go over from the first child all the way to the last child. In array, you can just use a loop and use array indices. But for singly linked list, you're going to start from the head and use the next reference, right, to traverse the list, right? That's the only difference. And we just got some auxiliary variable here, just about how many children we have maximum. Remember the distinction between array and also linked list. For array, you have to have a fixed size in the beginning. So let's say we'll go up to 10 children. And also we have a counter here, number of children. I'll talk about this counter in just one moment. Okay. Okay, so NOC here. Once we create one example, I'll show you how NOC can be interpreted. Okay, but you just record the number of children. But there's more to it. And then the constructor. The tree node constructor, we simply give the element for the root. Okay. So this is to create a singleton tree. So this is to create a singleton tree, where we're going to pass the elements, and then the root has the parents null. Right? Remember, the root is the only node that has null parents. Right? But sometimes it could be possible you can set a parent to be null for the moment, and you can set a parent references later. That's also possible. Right? You got to give yourself some flexibility. And this line here is to initialize the children array. All right? This one here, let me discuss that a little bit later. Okay, for sure today. I'm going to show to you exactly how to understand this line. It looks very daunting, but I'm going to explain to you. Somehow it's like a workaround you have to go with if you program in Java. But I'm pretty sure for other OOP language like a C# or maybe C++, it's very likely going to write something like that. Okay, and you simply initialize the counter to be 0. And you got other methods. You can simply get the elements for this particular node, and you can get the parents, get the children, and then set the elements, set the parents, at one child, remove some child as a particular position, which we covered earlier as well. Okay, so these are so that will be a skeleton for a tree node. Let's go a little bit further to see how we can set things up. Okay, let's say this. Let's say this is the structure we want to have. Let's say we have a node right here. Let's call it N. Okay, so we're basically creating a tree node object N over here. And let's say this node here is ought to actually have some parents. Okay, P. So that means the parents reference should be set to P. Okay, that's going up. And then let's say we have 2 children for this particular node. Let's say this will be child number 1. Let me call that C1. And we also got child number 2, right? Simply in array. You can get as many child as you like, up to 10. Okay, so this will be child number 2. Let's say that's a setup. But how do we create a runtime structure? Okay, let's start with the parent side, the predecessor. So this successor over, this predecessor here, the P, you can imagine that there is one node right here. Okay, so this will be the P. And this will be a tree node right here. And then you also got its parents, elements, and also children attribute, right? Let's just ignore the detail just for now, right? Similar structure. But we want to make sure the N here has its parents set to P. What should we do? We simply say, and the parents should not be assigned to wherever P is pointing to, right? That's the main point I'm trying to make, right? So I'm saying that the parents should really point to wherever P is pointing to, right? So now we're setting the parents. And then for C1 and C2, now we talk about multiple successors for this particular tree node. And this will be the first child at index 0. This will be the second child at index 1. Okay. Let's use different color here. Let's say C1 over here. So that means this is going to point to some tree node right here. And similarly, let's say C2 is going to be index 1. This will be another tree node. Okay, C1 and also C2. All right. So the main point to really understand here is, given a particular node, it is very possible you got to go up to its parents. Maybe you can go all the way up to the root, whose parent is null. And if you go down, you're going to go to traverse each individual child nodes from index 0 all the way to the maximum index. Well, the index is not null. And then you got to go for each child nodes, which might be subtrees. All right, I'll talk very quickly about NOC here. It's about the number of children currently. You can see this is child number 1, child number 2. So that means at the moment, the number of, so n here, n dot number of children will be equal to 2. We got exactly 2 child nodes. Whereas, presumably, all the remaining slots over here will just be null. If I now want to add a third child to the child list, which index should I go for? It should be index 2, right? Because that's the very first one that's null. So the NOC here, the 2 here, is telling us 2 things. Number 1, the number of children at the moment. Number 2, the index for the next child. Because if I want to add one more child to this node here, I need to go for index 2. And after that, I should really increment the 2 to 3, and etc. Right? So if you go for the array implementation, you just got to make sure you update this counter here appropriately whenever needed. Okay? Questions up to now? Okay. And then you can definitely compare about a previous reference and the next reference. You can think about here, going to parents is a little bit like a previous. And the next reference here, a little bit like a children, but in the tree case, it's definitely more general because it's not a unique child nodes you will get to. You just go to a linear collection of the child references, not just a unique next reference. Right? There's a critical difference. Okay. And then let's now talk about how we can construct the tree from the test cases. Now you'll be more precise. Okay. These 3 lines, we're creating basically 3 tree node instances. We got Agna, Elsa, and Anna. And here you can see the E here has been instantiated. Think about the string here. The generic parameter E has been instantiated. E instantiated to string. But doesn't need to be just string. It can be person, can be integer, can be any type that you like. For this case, it's simply string. Okay? Let's see how we can set this up. So one way to go is you simply create all the nodes in isolation. And then you set up the child and parent references. Very similar to when we set up the singly linked list earlier. You can create all the nodes and set the next references accordingly. Right? Similar. Okay. So let's now take a look at this one here. Okay. Okay, the first one. Let me highlight. Okay. Node number 1. Node number 2. And then node number 3. Okay, 3 nodes. Let's create these 3 nodes. They have nothing to do with each other to begin with. Okay, I do have some skeleton right here, right? Let me just use that. I got 1 node here, And I got one here. And I got another one here. Okay. You can see each one of them has the exact same structure, right? They got parents, element, children, and array. Right? The first one is going to be green. Okay, let me just, that would be green. That one there is going to create with elements ACNA. That's the only thing. All the other references would just be null. I'll show to you. Okay. So this one here, the parents would just be null. And the elements here is going to be a string, ACNA. Okay. So the array here, if you go back to the constructor for the tree node, when we first create the tree nodes, we have to initialize the array to be certain size. Okay, I'll talk about that particular line maybe after the break. But before the break, let's finish off this tracing quickly. Okay. So this will be the array that we initialize. Every slot here will just be null. Right? Let me omit the writing. Just imagine when you first create a tree node, there's no children, and the NOC will just be 0. So you can think about here, the NOC will just be 0 to begin with. And eventually, it's going to become 1 and 2, etc. And the other two, Elsa and Anna, they will be created in a very similar way. Okay, let me just put a reference here. So this node here is ACNA. All right, and then let's now put, this one will be the first child. That's going to be pink. All right. And this one here will be orange. Okay. And the pink node is Elsa. And similarly, the parents will be null, and the element will be Elsa. And Elsa dot NOC will be 0 at the moment. Okay. And for Anna, right here, almost identical. So this will be Anna. The parents will be null for now. Elements will be Anna. And Anna.NOC, I'll put it underneath it. Anna.NOC will be 0. What's our goal here? Our goal is to create this particular tree. We want to have ACNA being the root. And then we have Elsa, and also we have Anna right here. And we want to set up the reference in such a way. This will be the child reference going down. Symmetrically, if ACNA, let me say it again. If Elsa is one of the children for ACNA, that means Elsa going for her parents will also be ACNA, bidirectional. Okay, so that's something we're going to set it up. Okay. So think about the purple one here is about a child reference. But we also got one reference back. That one there is about the parents. Okay, that's something we'll see how to set up. Yeah, question?
Why don't we have the set parent stuff in the add child and vice versa? Why are we not having...
Oh, yeah, it's a very legitimate concern. Yes, the fellow student's question was, wouldn't it be simpler if you simply put as part of the add child method there to really set the parents accordingly? Definitely, that's one possible implementation. Because I'm creating this example here just for in-class illustration, I want to show you how to set it up explicitly. Yeah, so I would say the safe things to do. So look at the starter code you're given for assignment number 3 and see if there's any bidirectional setting over there. If this is already, that means you don't have to worry about them in the programming test. Otherwise, you may have to do it by yourself. Okay, good. Okay, let's just go with this version here. Just make it more explicit about what you need to do. Okay. Let's now try to understand about these 4 steps. Okay. So let's say number 1. Okay. We say ACNA.addChild Elsa. Okay. ACNA add child, that means it should be index 0. That we should really add this particular child. And it should be Elsa. That means Index 0 is going to point to wherever alpha is pointing to. This will be number 1. Okay, and you should update NOC from 0 to 1. The second child should also be stored at index 1. Okay. Let's move on. Step number 2. ACNA the add child Anna. Very similarly, so ACNA the same node. Now index 1 should be storing the second child, and that should be Anna. So index 1 should point to wherever Anna is pointing to, right? You can see Anna is right here. So we should update NOC from 1 to 2. So this will be step number 2. So far we have set up the children references, but we're missing the other direction, right? So far right now you can see the parent references for Elsa and Anna are still null. We want to set them up properly, bidirectional. Okay, let's do it. So number 3. Number 3 here. Okay. Elsa the set parents ACNA. Okay. Elsa parents currently is null. Rather than pointing to null, is going to point to wherever ACNA is pointing to. Right. Let me just try to go this way here. Right. So that's the parents link for Elsa. So this will be number 3. And then next one will be also very similar. Anna the set parents to be ACNA, the same parents. So that means the parents, rather than pointing to null, is going to point to this object here. Let's make it more explicit about this bidirectionality. Okay, I'll just go with one of them. So you can see for ACNA, and then if we follow up with the children, index 0 points to Elsa. Symmetrically, Elsa, the parents, points back to the same node for ACNA. So that's bidirectional. Always make sure when you try to implement a structure like a tree, you have to make sure bidirectionality to be maintained. And you will just have some assertions over here to be checked, right? Just look over one or two of them. ACNA, the get parents, remain to be null because that's simply the root. And then ACNA will be Elsa the get parents, right? ACNA pointing to this object here. Elsa the parents pointing to the same object, aliasing. So equals. So this is the aliasing. Okay, you guys can go over about the rest of the assertions, just double check. Right? If you look at the diagram here, when you do the tracing, and you should be able to check each one of these. Right? So one possible question you might be given in the exam or maybe in the written test is, let's say we do some setup for the tree. Afterwards, what JUnit assertion should pass and what should fail? Things like that, right? You want to be able to trace them. Okay. Guys, any questions before we take a short break? All good? All right. So you can we cannot really cover too much code in the lecture, but hopefully this will give you enough like intuition and background for you to do the assignment number 3. All right. All right. Let's now take a short break. And so the only thing left about the Java code that we talk about for the tree node is how you can initialize a generic array. I think that's good for your knowledge for Java anyway. But I would suggest, let me go on with the other stuff for today first. We'll talk about this particular workaround. It's kind of boring, but we need to talk about it. Either we'll talk about this at the end of today or maybe in the beginning of Thursday, either way. Okay, let me skip a little bit just for now. Okay. Let's talk about this one here, which I will require more of your attention about how you can do a recursive method on the tree node. So how do we calculate the depth given a tree node, for example, right? So this is a code that's made available on the lecture site. Please do download, import to Eclipse, and play with them. It's also going to help you to understand about recursive methods on trees in general. But this one here. Let's say, for example, this test case, I want to do, let's say, this line right here. Assert equals. All right. I'll make it a bit bigger. Okay. So we are saying that we have a utility class, and then we call the depth method here. Okay. And then we want to know what's the depth of this particular node for Vanessa. And it turns out the expected value for the depth that's returned should be 3. Let's verify diagrammatically. Right? You can see Vanessa is here. Why is the depth of this node storing Vanessa 3? Because 1 link, 2 links, and 3 links, all the way to David, right? That's 3. But how do we compute this recursively? That's the question, right? So you can definitely go over this test case after the class. You can see there are various cases you can look into, right? I'm going to trace one of them in detail with you, but you can look at others on your own. Okay? Let's look at the method here. This node here will be the action node. We want to calculate the depth for, let's say, node n. So in this case, Vanessa is simply n, right here. So think about the n here is really Vanessa, okay? And there are 2 cases here. This will be base case, and this will be the recursive case. Let's analyze a little bit, and then we'll go on and calculate it. This part here will be the base case. If the current node that we are looking at has its parents being null, what does that mean? That's the root. For example, if I say I want to calculate the depth of David, David.parents is going to be null. And in that case, I don't need to calculate anything further. The depth for the root should just be 0. Right? Just make sure you understand the base case. So this part here, let me highlight it. And get parents equals null tells us n is the root. In that case, the depth of n would just be equal to 0. Okay, base case. And recursive case would be if somehow the current node I'm considering, for example, Vanessa, is not the root. What should I do? What I do is I'm going to use the link, parent link for Vanessa to count as 1. And then I'm going to recursively calculate the depth of its parents. This will be the depth of Vanessa's parents. And add these 2 numbers together, conceptually. But we're going to trace it, don't worry. Okay? Let me draw a little bit better, right? I was just hand waving a little bit, but let's now try to draw it, and then we'll calculate it. Let me draw this aside. Okay? So if I want to calculate the depth of Vanessa, okay? Think about Vanessa is at the bottom of the tree. Vanessa over here. And then I know that by following the link right here, this is 1. Think about the 1 here is the 1 over here. And then there might be something along the way, like an ancestor path, all the way to the root of the tree. Okay? You can think about. So go all the way up to the root. This will be the root. It could be arbitrarily long, right? Because Vanessa might be a very deep node onto the tree. So this part here is just going to be the depth of these parents. Okay? Get this number here, and then get this +1 and plus them together, right? So that's what you will get eventually. Okay, conceptually, that's how we calculate. But we're going to see how exactly the recursive call is going to unfold. Okay, let's trace that together. Okay. Right, this one here is more like a conceptual idea, which might be useful, for you to sketch on a piece of paper before you start coding the method. But let's say we got the method coded up. How can we trace it? Let's see. Okay. So we start with the depth of Vanessa. Okay, so we start with right here. We want to calculate the depth of Vanessa. And we're going to check to see Vanessa's parents, right? You can think about we're going to check to see whether or not Vanessa's parent is null. Apparently it is not, because it has the parents Elsa. Right? Vanessa's parents is not equal to null. So we have to do recursive call. So we go to the else part. In that way, we're going to have 1 plus, which will be equal to 1 plus the depth of Vanessa's parents. The depth of Vanessa's parents will be Elsa. Are we okay so far? Okay. Let me repeat this part here because it's going to be repeated a few times. I want to calculate the depth of Vanessa. It's not the root, so I have to calculate it recursively. I'm going to say calculate this link right here, and also recursively calculate what's the depth of Vanessa's parents, which will be Elsa. Once this answer is known, we can plus 1 and get a final answer. Okay. Let's now try to calculate this part over here. What's the depth of Elsa? Elsa here, and then we're going to check. Elsa's parents is Chris, which is not known. So it's not base case. Elsa's parents also is not equal to known. So we know that for this part here, it's going to be, again, the recursive case, which will be 1 plus the depth of Elsa's parents will be Chris. Okay? Okay. So you can see so far we got 2, 1 already. So this is just another 1 there. Okay, so we are now going to calculate another one. Let's say Chris. What will be the depth of Chris? So we're going to check to see whether Chris' parents is equal to known. It is not, because Chris' parents is David. Okay, so here we're going to have Chris' parents. You know what? Let me make this a bit smaller. We just need one more level. Okay. Okay, let me just make this part here smaller. Okay, that's right. Okay, for Chris, we know that the parent is still not equal to known, so we're not there yet in the base case. So Chris' parents also is not equal to known. So we should really go to this else part over here. And that one there is going to be 1 plus the depth of David. All right, so we got another link of 1 right here. So this will be the final bit because we know that David here is the root of the tree. So this part here is going to satisfy the base case constraint because David again parents is going to be known. So just return 0. So this will be 0. Right? And after all, how many plus 1 do we have? 1, 2, and also 3. So we'll get 3 as a result. Right? 1, 2, and 3. So that will be 3, which is what you see over here. All right, any questions? It's a very simple one, but it's also important for you to see how you can trace it. For many of the recursive methods you're going to implement, you're going to need to do some unfolding about how you can reach all the way up to the root to get to the base cases. Okay. Everybody's good? Okay. One little exercise for you. This one will be a little bit more complicated, but I do have some solution walkthrough video for you, okay, which is about calculate the heights of a tree. Okay, so this will be exercise for you. I would suggest, first of all, try to study the code itself to see how that works, and then you can look at the Java JUnit test cases as well, okay, to see how to trace the height of Chris, for example, right? So we talk about how you can calculate the height of this particular subtree. We spoke about it last Tuesday. And how can you find a solution? So you can go to the lecture site. Let me show to you. It's right here. You will see under exercises, computing the heights recursively in Java, right? That's tracing exactly this one here. I would suggest try to do that on a piece of paper like how I did it for the depth question. And then try to compare your answer. Or you can just go directly to the solution. That's fine too, right? Just make sure you cover this properly. I think that one is going to help you also for the recursive tracing. And this one is going to be more complicated because we do involve a loop. And so the number of recursive calls you have to make depends on how many iterations you're going to run for the loop. And I think one of your assignment ones questions about running recursive call inside a loop, right? Like a stair climbing, right? Similar, right? So guys, I'm going to leave this exercise to you, right? You got to make sure follow it and then make sure you do it. Okay? Right, so up to now, it's about a general tree discussion. But now we want to narrow down our focus more so we can do more mathematical properties derivation, which is about binary tree. Okay, we're going to cover a little bit about binary tree in 20 minutes. Okay. Okay, let's see where we are. Okay, so we got depth over here. And also we got the heights for the tree. And that'll be exercise for you. Okay, some more exercises. You can definitely take the exercise code I gave to you on the lecture slide and try to extend it, maybe with 2 more methods to implement for yourself. Right? Just more exercises for you. All right, let's talk about binary trees. Okay, what's really a binary tree? So we kind of narrow down from general tree into binary tree. What's really the extra constraint we're imposing? So binary tree, first of all, is an order tree. That means the order for the children, like for example, first child and second child, they matter. Okay, so you talk about first child, and you talk about second child. Okay, here is one constraint. Every node has at most 2 children. It can be 0 child, in which case it's an external node. You can have 1 child or 2 children, but not 3. Okay, so that's a constraint. And we say that we got left child and right child. For binary tree, you don't really say the first child and second child. You say the left child and also the right child. And left child should go before the right child. And we got to visualize it. Okay, and then we just got different cases. Either the tree can be empty, or it can be a singleton tree containing only the root, or you got left child and right child, right? Let's now visualize it to see what's going on. Okay. Very similar as before. Okay, so there are 2 base cases. So we got case 0, empty tree, no node. And we got case 1, it's a singleton tree. In which case we got the root only. Okay, and then we're going to look at case number 2. When we got 2 or more nodes. Case 2, we got 2 or more nodes. All right, let's see how we can visualize it. Not really the coding level. I think abstract level should be good. Let's say we got a root right here. Actually, maybe make a node, like a circle. Let's say this is the root of the binary tree. It's an order tree. So we got left child and right child. So there should be a reference called left. In which case, it's going to be another node right here. That'll be the left child. And we have the right child, which would be the second child. And that would be just another node. And each child node is going to be the root of another subtree. Right? There are only up to 2 subtrees for each node. So think about this one here is 1 tree. And this one here is another subtree, right? And we have a special name for those. This is so-called the left subtree of, let's say the root here, let's call it n. Of n. And the purple one here will be the right subtree. Right subtree of n. Okay, left subtree, right subtree. In some way, when you want to make a recursive call, or when you want to solve a problem recursively on binary tree, you don't really have to go through an array of all the children, because in the general tree case, you have arbitrary number of children. But for binary tree, you only have to go for left and right. You don't need to go more than that. So in some ways, it's a bit simpler, right? And also important for you to note right now, this one here is a binary tree. This purple one here is also a binary tree. In order for me to solve a problem for this strictly larger binary tree, I can say I want to handle the root. And then I can solve a strictly smaller problem on this smallest binary tree, which is the left subtree. I can solve the same problem on this strictly smaller problem, which would be the right subtree, and then combine the result with the root. I can solve the bigger problem right here. Right? Very similar. Okay, we're going to see one example right away. Any question about this visualization here? Very important, right? You got the root, you got the left child, which will be the root for the left subtree. Also, you got a right child, which will be the root for the right subtree, right, etc. Okay. So there are two problems over here I got on the notes. This one here, just about counting the number of nodes. This one here is something basically we did last week. Last week, we actually tried to do on a general tree. So the way you count the number of nodes in a binary tree just identical to how you calculate the number of nodes in the general tree. So calculate how many nodes are there in the left subtree, calculate how many there are in the right subtree. This plus 1. You got it. All right, so I don't need to waste your time. But you can definitely take a look on the clean page and try to see how you can work it out. Okay? Let's look at this one here. That's kind of interesting. Okay? Let's say we want to do searching. We want to define a method there. Okay, I'll maybe write it down. Okay, and we'll see how to do this. Let's say we want to search. And we want to start with some root. I can start with A. Okay, so that means my search should really start with some root, which is A. Let's say I'm looking for whether or not G exists in the tree. It does. It does exist in the right subtree. So that means in this case, it's going to return true. Another run. I will start searching also from the same root, A. And then I want to search for, let's say, Z, which doesn't exist in the tree. In that case, it should return false. Right? So that's good, right? Just to get some intuition about what this method should do. It should either return true or false, a Boolean result. If the we're going to start with some note. Okay, let me just make some quick notes for you. Think about the A here. Is saying that the search starts from here. Search starts. And G and Z are the contents we're looking for in the tree, right? Either true or false. Okay. Conceptually, anyone want to suggest how we should do it? Anybody? Go ahead.
So whenever we get true, we just switch our attention to the node where it returned true, and then examine the subnode.
You definitely got to explore the subtree, right? So let's put it this way. Let's say I'm searching. Starting from A, I'm looking for A. What does that mean? I'm looking at, this will be the starting point. If the starting point already got the contents matching what I'm searching for, do I need to bother to go for left subtree or right subtree? I don't need to. I can return true right away. That will be the base case. If I find the one I'm searching for right away, that's a base case. Why don't we write it down first? Okay. So if I say, let's say, the search method, which is going to be a Boolean method. So search. I have some tree node. Okay, let's say some root. And then I have some element, generic parameter. And then I would say data. I'll say D for data. All right, let's say. The base case would be if the root I'm looking at dot get elements dot equals, right, the equals method in Java, and then D. This means I found it. I don't need to go for any further recursion, right? I can simply return true. Okay, let's highlight this base case over here. Everybody follow the base case, right? If I found it right away in the root, I don't need to go any further recursion, right? Base case. What about recursive case? Let's say I'm searching for Z, or let's say G, let's say. I'm searching for G here. G is not really matching the starting point. What should I do?
You return search left subtree or search right subtree.
Which one should I go? In the worst case, do I need to search for both trees, or it is okay just for search for one branch? Go ahead, yeah.
I think one is right because it's ordered.
Okay, let's say here, right? Let's say I'm looking for G, right? So in this case, I know it's in the right branch. I can just go to the right. But what if I change this maybe to J? In that case, J is actually in the left branch. So depending on what this content really is, it could be in the left or it could be in the right. Or it could be that it's something that doesn't even exist. But how can I confirm it does not exist? It does not exist because I cannot find it in the left branch. Also, I cannot find it in the right branch. So this tells me that in this searching mechanism, I need to go, in the worst case, both branches. Okay? Good. Okay. Now I'm going to write down something, okay, for you to think about. Well, this one is not exactly precise, just conceptually. Right? Because sometimes you may have, let's say, it's possible for a tree only has the right child, but for the left child, it's simply just null. It's possible. And symmetrically, it is possible you don't have the right child over here, and then you got a left child. So there are many different cases, depending on how the input tree is being set up. Right? We want to keep it as general as possible. We want to say, if there is a left child, I'm going to search on the left subtree to see if the contents I'm looking for is there. If it is already there, I don't need to waste time on here. I can just return true right away. On the other hand, if I try to search on the left subtree and the element is not there, I should really look at the right subtree as well to see if it is there. Right? So let's look at just one line implementation. Remember the short circuit evaluation that we spoke about. Right? Okay, so short circuit evaluation. I'm going to write it down. Okay, short circuit evaluation. Okay, and let's say this one here is, you think about this is the root. This will be the root dot left. Okay. And then this part here, the root here will be root dot right. But in general, root dot left or root dot right might be null. Could be, right? So what I will do is, I'm going to write here. Otherwise, I'm going to return a one-line expression. Okay? I'm going to say, I may have to look at the left result or the right result. If you recall about what this OR operator really means in short circuit evaluation. Anybody? Go ahead. Go ahead. Yeah. OR. Yeah, exactly. Yeah. If this one here is actually true, I don't need to waste time. That means it has been found. If this one here is actually false, I need to check this one just to be sure. Right? Good. Okay. Very good. Now for here. However, I should only search for the left if there is such a root. It's not null. Right? So I'm going to say here, r dot left not equal to null, and I'm going to make a recursive call here. Search. Because it's not null, I can say r dot left, and then I'm going to search for the same thing, D. All right. And then this one here, very similar. It's going to be r dot right not equal to null. If that's the case, I'm going to go ahead and search for it. And that should be r dot right, and then the same thing. I'm just running out of space, but you see the idea. Right? So now, what can be returning false? For example, let's say in this case. In this case, this is going to trigger some false return because, first of all, r dot left is actually not equal to null. That means I'm going to go ahead and search for the left. Does z exist in here? No, it does not. So that part there is going to return false. False for the OR here, you're still going to go to the right-hand side because short circuit evaluation. And then when you go for the right-hand side, let me just go there and show to you. Okay, I think it's better to write it down. I think we've got about 3 minutes. I think that'll be the last thing I'm going to talk about today. Okay. If you try to trace the search A and Z, okay, 1A, we know that A dot left is not equal to null because you can see that it's B. Okay, and we're going to call recursively search A dot left and searching for the same thing, which is Z. So A dot left, we know that it's B. So think about this recursive call here. It's just like a subproblem that we are trying to solve from B. And this one here, the subtree rooted at B, does it contain Z that we're looking for? No. So it's going to be false. So that one there is going to return false. And so this part over here is going to be false. Short circuit evaluation. For the OR operator, if this one is false, you still got to evaluate the right-hand side to see either that's true or false. Okay? So that means we got to go over to the second branch. So 2A, you're going to look at the right-hand side. A dot right is not equal to null because you can see it's C. Right? And then 2B over here, you're going to make a second recursive call, which is going to search A dot right and then Z. Okay? A dot right, we can see it is C. So this recursive call here, again, let me highlight it. This one here, see the subtree. Does Z exist over there? No, false. So that would mean we got another false. So this whole thing over here is going to be false. So what we get is for this OR here, false and false. Overall, it's going to be false. So G doesn't exist. Okay. It is important for you to kind of see how this like a binary tree search is going to work. Later on, we're going to see a slightly different search on the binary tree. It's called binary search. If we can somehow organize the contents in a particular way, we don't need to search for both branches. We can only go for one branch. Right? But this one here is like a general search. Right? I'll make a point here and then we're done. Okay? Just give me 30 seconds. Okay? For your test and for your exam, when you prepare for that, right, just compare. Compare this search with binary search that we're going to talk about later. They're different. If you can organize the contents of the nodes in a particular way, you don't have to look for both branches. Okay, we'll see. Okay, exactly. Guys, any questions? Okay, we're now diving a little bit deeper into the tree content. So starting from Thursday, we'll talk something more mathematical. Just get ready. All right. Okay, I'll see you guys.